When input dimension is very high, then the vanilla gradient descent, the simple gradient descent algorithm can have very slow convergence rate. Why? So I will give you a simple example where there are only two input predictor or input parameters, theta 1 and theta 2. Okay. So in this case, we can draw some contour that present the same loss function value. Okay. Right. Now let's consider we want to find the optimal point here from let's say this initial point. Okay. So for this initial point, you will learn some gradient descent algorithm, a gradient descent algorithm with a constant step size gamma. Then you can see a huge gradient for this axis, the y-axis or vertical axis, but very small gradient for this horizontal axis. Okay, so your update will move a lot to this direction, but will move to very tiny amount for this direction. Okay, right. Yeah. So at this point, this is fine because we want to go here. We want to go to this optimal point, and we really want to move to this direction, right? So currently it's fine, but as soon as you arrive this point by gradient descent, let's say, from this point, the gradient is very tiny. So to converge here, you have to update a lot of iteration because the gradient is very tiny, right? So in this case, maybe it is better to increase the gamma value. You have to increase the gamma value, maybe. But the problem is, it is hard to control your step size gamma adaptively to the current function value and current function shape. Okay. So one possible way to do this, of course, there are many optimization theories, and there are many studies on this optimization problem, and many interesting and very nice algorithms are invented based on Hessian. Hessian is a second derivative matrix. Okay, so when you know what is Hessian and when you can compute the inverse of your Hessian matrix, indeed you can very nicely control the step size, and you can very nicely control the gradient direction so that your update can converge to the optimal point with a few iterations. Okay, but with deep learning, we cannot utilize such very advanced optimization technique. The main reason is the Hessian is very huge. Hessian is a matrix, and when we have millions of parameters, we have to compute the Hessian matrix millions by millions entries. So it is impossible to store every entries of Hessian. And worst thing is it is almost impossible to compute the inverse of Hessian, which really required to compute for update your second order gradient descent algorithm based on Hessian matrix. So The computational complexity of this type of approach is very huge, so this is not allowed in practice. Okay, so to overcome this type of issue, recently or few years back, there are some interesting idea called Adagrad, momentum, RMS probe, among others. There are many variants of gradient descent algorithm. They basically prevent some oscillations due to huge step size, and they want to give good scales to each coordinate. How to prevent the oscillation? The main idea is kind of moving average. So essentially, when there is some oscillation to this vertical, the horizontal axis, and when you take the average, the oscillation will cancel out, right? For the scale to each coordinate, they usually compute the scale of partial derivative, and take some average, so that we can know the gradient scale for each coordinate, and then divided by square root of sum of the square of partial derivative to each partial derivative, something like this. Then essentially with this type of approach, you can well scale each coordinate so that every coordinate share almost same value range. Okay, which is very nice in practice. And empirically, there are many evidence these two technique, moving average and this second order scaling, can provide very nice convergence behavior.